Okie dokie. So, okay, so we're ready for this slide. And I kind of wanted to, this is a really neat topic, so I didn't want to rush, kind of squeeze it in on Wednesday. So if you've ever heard somebody talk about the dark side of the moon, well, to me, that something's not quite, they kind of are confusing the dark side of the moon with what we call the far side of the moon. I always think of that show Far Side. It has nothing to do with the moon, but that. Anyway, so the far side of the moon looks like this. Here's the deal, and I think this gal did a pretty good job again. This young lady is the moon. The thing in the center is the Earth. So we know now that the moon orbits the Earth, right? So the way you look at this figure is, can you see where her front, you see the front of her is always facing the Earth. The front of her is always facing the Earth, okay? That is what we call the near side. If she's the moon, that's the near side of the moon, okay? This is the far side of the moon. Let's see if I have any more words to put it up. So here's the deal. So notice, and I'm going to kind of just do exactly what she's doing. I am the moon, and I'm going to orbit the Earth. I'm going to go a quarter. How long does it take to go 1 quarter around, for the moon to go a week? Very good. 7 days. Okay, and it's a subtle thing, but can you see me kind of twisting? Okay, and I'm just like her. Okay, I twist it a little bit. My face is still the same side of the moon is towards the Earth. Okay, I'm going to go 1 more week. Okay. I'm going to go 1 more week, and I have to twist a little bit. And actually, if you were to kind of track my rotation, okay, the time it took me to rotate was exactly the same time it took me to orbit. Okay, we call the rotation and the orbit is in sync. It's the same number of days. And the consequence of having in sync rotation and orbit means that the same side of the moon is always facing the Earth.
So the moon never does like a 360-degree angle like the Earth does?
It does a 360, but it takes about 28 days to do it. So as I was doing this, I was kind of spinning too on my axis. And if it takes me 28 days to complete 1 orbit, it takes me 28 days to complete 1 spin. It's the exact amount of time. I know, you're like, there's a lot of things in astronomy I have to think, now really, how does that work? Seasons still.
Yeah, I mean, just because like if we only see one side, then if the moon does like...
If the moon, for instance, if the moon pirouetted, that's the right word, but that swirled, rotated twice, okay, for every orbit, it would kind of look like, let's see, how do I want to do this? It would look like, I want to say, I'm kind of thinking maybe like that. No. And then we would see the backside. Okay, I probably did more than, okay. Yeah. So just to kind of emphasize what we got here, we would call this the near side. Sorry to write on your front like that. And we would call this the far side. So sometimes people get it wrong and they call that the dark side, but it's not really dark. Case in point. So let's keep kind of how we have the Earth and the moon, and we'll turn this back into the sun. It's like Cinderella's fairy godmother, who she turns things into things. Okay, anyway. Okay, so that's the sun. Okay, so here's the deal. So I did this like she did this. So what phase of the moon am I in right now? Not new. If the sun's over there. I'm in a full. Yep, full moon. Okay, and this would be waning, and this is last quarter. And so what phase is this? New moon. Very good. So my point here is that the far side, is it lit up? Yeah. And over here at full moon, is the far side lit up? No. So I mean, the far side and the near side kind of get, their same fair share of sunlight. So, all right. I just think that's pretty cool. So you guys don't have this slide, but what do you think? How many people think, I'm going to ask you which moon looks familiar. If you saw the moon last night, how many people think that this left one is what we see when we look at the moon? It is. That's the near side. Exactly. Near side. Okay. What's different about the far side?
It has a lot of craters.
It does have a lot of craters. And that's not by accident. Craters, like, we have pockmarks on the Earth, like craters like that. But the thing about the Earth is we also have, like, erosion things, like wind and oceans, and we have plate tectonics. So we have a lot of, like, what our surface of the Earth is like is very dynamic. So it's been fixed.
How big is the moon, like, in comparison to the Earth?
How big is the moon in comparison to the Earth? That's a good question. The gravity's about, I think, 1/6. So
I think it's an eighth of the size.
the eighth of the size? Okay. Sounds reasonable. Like the diameters or comparison?
I always thought it was smaller.
Yeah. It's a good question. I will look it up and post it on my Twitter feed. Or he's going to Google it right now. Let's ask Siri. Tempted to, but watch this.
Wait, so what side did
10. Very good. Okay. So where did Neil Armstrong land? He landed on the near side. And I'm not...
Where at?
What's that?
Where at?
There are maps that show you where at. And we looked for the flag last night, could not find it. Seriously. But the landings in general have been on the near side. And I'm kind of thinking that's a communication issue. About the time you put something on the far side, you have an issue with regard to communicating with the Earth. But I think I told you already that there is a terrible science fiction movie out there that talks about landing over here. And in that movie, I'll go ahead and tell you, they find like a Russian lander already there. And in that movie, they all
Was it
die.
like Apollo 18 or something?
Oh, yeah, I think so.
Yeah, that was an awful.
It was bad.
It was really bad.
Don't watch it.
Yeah,
It was very bad.
bad.
So the last topic I need to cover actually is going to be very pertinent in October, because in October we are going to be privy to both an eclipse of the moon and an eclipse of the sun. And I have an idea how you guys can safely view the sun. It's been out there forever, the whole projection, the pinhole box. So I'm going to post instructions so that you guys can safely view the eclipse for lab credit. So classes should be a balance of, oh, that's cool, and oh, good, I got lab credit. Okay? So I'll have more details for that coming up. So eclipses, and not so surprising, or you may have already been wondering, for instance, if I'm over here, you guys told me this is a full moon, right? But if, I'm going to kind of move this, so the trash can. But here's the deal. Did you see where I kind of directly lined up the sun and the earth and the moon? Doesn't it almost seem like the moons, that the sunlight might be blocked out by the earth? Yeah. That is called a lunar eclipse, and it happens. But it doesn't happen every full moon. I'll tell you why at the end there. Okay? Kind of similarly, you guys told me this is new moon. The moon's lit up, but the lit up part we don't see. Okay, this is new moon. And honestly, if this really does happen, it's going to happen partially in October. But there are times during a new moon where the moon blocks out, the disk of the moon blocks out the disk of the sun. Okay, from our perspective. We call that a lunar eclipse, or excuse me, a solar eclipse. Okay. So we're gonna take, let's see, is it here? Yeah. This figure is showing two shadows. Actually, maybe just one shadow. No, two shadows. This figure, can you clearly see that here is the daytime side of the Earth. This is the nighttime side of the Earth. We all good with that? Okay. Daytime and nighttime side. Okay. If you stand in the middle of nighttime side and look into outer space, basically we have a cone of shadow that the Earth is creating into outer space. Okay, it's basically taking that sunlight and blocking it. Happens all the time. If you were to take a light bulb, turn it on, and put your hand here, your hand casts a shadow into outer space. Okay? Same thing. Okay, this just happens to be the Earth that's blocking the sunlight to a region of space beyond it. So, here's the deal though, and this happens with regular shadows too. There's a dark part of the shadow we call the umbra, and there's a light part of the shadow called the penumbra. Okay? So there's the sweet dark umbra, and then there's the kind of dim penumbra, two parts of the shadow. Similarly, I think what this is trying to show you, this little point right here, no, I don't think so. I was going to say, I think that's trying to show you the moon. But, okay. So here we go. There are different types of lunar eclipses. So I guess I got to come back over here and be a full moon again, don't I, to make a lunar eclipse. There are different types of lunar eclipses. There's the one coming up at, I think it's a terrible time. It's like 4 in the morning. I think I have that right. 4 in the morning in October. But it's worth it because it's a total lunar eclipse. Have you ever heard of the blood red moon? Okay.
Not too long ago.
Yeah, there was one not that long ago. Is it cool?
It's pretty sweet.
Yeah, I agree. And the thing about it is like animals respond to it because animals do different things depending upon a full moon or a new moon. They just do. I mean, if I was an animal, I would. If I'm a nocturnal animal. And so, like at what we call totality, when the moon passes into that umbra part of the Earth's shadow, okay, it turns blood red and just kind of dims. And, you know, if you were a critter, you'd be like, uh-oh. Where'd the moon go? But then, so let me go ahead and animate it a little bit. Basically, if I'm the moon again, remember, I'm orbiting the Earth. Okay, what I'm going to do is I'm first going to pass it into that dim part of the shadow, the penumbral part of the Earth shadow. It's just kind of a gray area, not much to see, quite frankly. But when I start stepping into the umbral, the dark part of the bullseye of the Earth shadow, then you start to see some things. You can actually see a bite taken out of the moon. I love it. I love it. It's worth getting up for. I'm just saying. And I'm going to have to look at the details to see if I'm going to go out to the observatory and, or something. Okay, so
take pictures of it
along.
indoors.
I should take some pictures of it. Okay, and it passes in, and at totality, basically, the entire disk of the moon is hiding in the Earth's umbral shadow. Okay, and then of course it will pass out, and you'll see a little bit revealed of the moon, a little bit revealed of the moon. And then it'll go into the penumbral, so it'll be a little gray. I can't see penumbral eclipses, I really can't. And then it'll pass all the way out. So that's a total eclipse. So I hope you kind of got the idea that if somebody says there's an eclipse and it's 4 o'clock in the morning and the moon is just going to pass through the part of the shadow of the Earth that we call the penumbral part of the shadow, don't get up. Because it just barely kind of dims. A partial lunar eclipse is where at least you'll see a bite taken out. So that means just a portion of the moon is going to go ahead and pass into the Earth's dark shadow. Okay, so we have a total, a partial, and a penumbral. The first two, I might get up early in the morning. There was one a few years ago that was like December 11th or something. A total eclipse, lunar eclipse, and I got my husband out of bed and we went to the observatory and watched it, and it was really worth it. So it was like, I don't know, 20 degrees out or something. It was very cold. It was all worth it. So this is showing you the moon passing into, this would be kind of dim here, okay? Just kind of grayed out. This is where you start seeing a bite taken out of the moon. This would be totality, okay? Blood red part right here, and here it's kind of stepping out, so you'd see the bite returning. So, a penumbral eclipse, can't really tell it's doing much. Okay, so an eclipse of the sun can only happen in this configuration, in this sort of lineup here, when the moon is in its new phase. And so what we see is the moon casting a shadow on the Earth. and people see it. Actually, the moon casts shadows all the time relative to the sun. Okay, it just so happens that the Earth is in the way of that shadow that the moon is casting. So there's a few types of solar eclipses too. Now, the solar eclipse that we're going to see in October is a partial solar eclipse. So the deal with partial solar eclipse is kind of like shown here. Okay, this actually has to, this picture right here, this had to have been taken with a special camera. Okay, because anytime that amount of the sun's disk is showing, you have so much energy coming at you in the visible light. If this was the situation with the moon's disk passing into the sun's disk like that, okay, you could hardly tell that anything was happening. You can use welder glasses to look at it, I think. But what I'm going to suggest, and make sure that our lawyers are okay with this, is the whole pinhole projection thing. So basically, it's a box with a pinhole in it, and you can see what's going on with the moon's disk and the sun's disk projected safely inside. Okay, but also, it's on a Thursday, so about 3 o'clock for this eclipse, I'm going to set up the telescope up there and try to get a sun filter for my long one. I have authorization to purchase one, my husband said. Okay. So this will be in October coming up. This one is called an annular eclipse. And when the moon is dead center, casting a shadow on the Earth, the thing here is that, let me make sure I get this right. The thing here is, I want to go this way. We said the distance between the moon and the Earth varies a little bit. The thing here is it's just a little bit too far away to entirely cover the disk of the sun. Okay, so it casts a shadow, dead center, okay, but it leaves a ring. Okay, I hope that works. So the last slide here is to tell you why we don't see an eclipse of the moon every full moon, and why we don't see an eclipse of the sun every new moon. So the kind of cool thing about this, do you see these slanted kind of little circles here? Those are showing orbits of the moon as it orbits the Earth at various times. The flat part right here, this thing right here, is showing you the real orbit of the moon, the orbit of the Earth as the Earth orbits the sun. So this line, this orange line, I don't know why I pick orange all the time, but this orange line is the ecliptic. Okay? Earth orbiting sun, the ecliptic. These little circles are showing you how the moon is actually tilted, what we say, 5 degrees outside the plane of the ecliptic. So that has consequences. So one way to look at it is basically the moon kind of bobs up, or bobs down and up relative to the plane of the ecliptic, because its orbit is slanted. Okay, so we say the nodes need to just line up just right. Okay, so of course NASA's on it. They're always on it. Here, maybe, oh yeah. So for 2014, what I've been talking about, and yet there were a couple earlier this year. You can see the ones in October. So when you go to this web page, the October 8th is the eclipse of the moon, and October 23rd is that partial eclipse of the sun. Whenever you're looking at these, in order to kind of talk worldwide, they use a time called Universal Time, UT. And we are, depending on if we're on daylight savings time or off daylight savings time, we're 5 or 6 hours subtracted from that. So we shall see. Any questions? Okay. Let's go ahead and start the next chapter just a little bit. Okay. So this chapter tries to kind of put into perspective kind of the historic part of astronomy. Okay. This doesn't have to do with the historic part of astronomy, but honestly, if you were even on the day side of Earth, which I know this is the day side of Earth because I can see these blue skies, if you get beyond Earth's atmosphere, this is what it looks like if you're looking towards the sun. Pitch black. Okay, we need the Earth's atmosphere to actually give us blue skies during the daytime. Okay, that's kind of neat. And it's the gases in the Earth's atmosphere that bang or bounce the particular colors of light around. But we're going to end this talking about, or kind of talk to you about the scientific method and how the scientific method of solving problems, the scientific approach to solving problems, methodical, it's common sense. And actually, astronomy is like every other science. It started out, I say the science of astronomy, but the way the sky moved used to be kind of mystic and ununderstood. Not understood. Is that ununderstood a word? Okay. But now it's we apply science most definitely to what we see happening in the sky. Okay, so when I kind of end up with the method of scientific thought process, it's very what makes sense. So I would just emphasize, though, in science, we make observations, and we count on those observations, let's see, there are some natural cause. There's some natural cause at the crux of every observation. Let me see. Used to be, and I don't know if it was this bad, but it used to be if a ball was located at this position, 2 hours later, the ball is located at this position, before the idea of there's some sort of natural cause, it was like, oh, some sort of mystic thing happened to make, So, as far as observing patterns in the sky, that would involve patterns as the Earth spins on its axis. That would also involve patterns as the moon orbits the Earth. It involves patterns as the Earth orbits the sun. Okay, for eons now, folks have been tracking those things for practical reasons. Oftentimes, for farming. Personally, I think like some of those stories about the folklore, like Cygnus the Swan and Lyra the Lyre, that was entertainment back then. Okay. So it's been going on for a long time. And I think it's neat to kind of picture the different cultures basically taking their stories. Now, this wouldn't be science necessarily, but their folklore and passing the baton on to the next generation. I just think that's a good picture. So with regard to astronomy, your textbook really kind of focuses on this region of the world. Notice North America isn't here, right? We were babies back then. Okay, but if you read your textbook, I think they do a good job of saying how Alexandria the Great, who was a student when Alexandria the Great was in power, you're going to see on the next slide, he created a library, a repository, kind of like we call the World Wide Web now, okay, a place to put knowledge. And he was good at collecting that knowledge. I can almost just see him. But the problem is, rulers fall, and he fell. And when he fell, actually, you see why this is a reconstruction of this library. The library was demolished. It's like, oh my gosh. All of his collecting wisdom at the time. So kind of after the destruction of the Alexandria's library, the baton was picked up again by the Islam, people of the Islam faith, I want to say. Okay, and they created another library. So they started collecting stuff. If you read your textbook, one of the things that might strike you is clear back then, in this culture even, scientists were shaking hands across the boundaries that otherwise, politically, they couldn't shake hands. Do you know what I'm saying? Scientists are all like about, hey, I don't care. I want to kind of connect the dots here. I want to create a repository for everybody to come see. Okay. So you don't have the slide. I will make this. There's a few slides that says Chapter 2, from Chapter 2, and I'll make them available to you. But all this slide does is kind of, in one lucky morning, you can actually see all 5 planets that folks back in the time of Copernicus, folks back in the time of Ptolemy and Kepler, those are names of famous people in this area, they could see these planets, okay? So it's kind of cool. Mercury, Venus, these guys are always like kind of close to the sun at sunset or sunrise, okay? And then Mars, Saturn, and Jupiter. Of course, are they ordered like that? Is that the order of them? Not quite, almost. This is actually the inner planet, then Venus, Earth, Mars, and then Jupiter and Saturn. Okay, so I'll go ahead and make that slide available. You have this slide. So there was a lot of hurdles that needed to be overcome. There are always hurdles to overcome in all sciences, okay, including astronomy. But these great thinkers, you've probably heard of Plato and Aristotle. Okay, these great thinkers, one of the things, the premises that they were under the guise of, and they were beyond these guys too, is that the heavens are perfect. Okay, all religion aside. Okay, heavens were perfect, and the shape that's perfect is a circle or a sphere. Okay, and you don't have this one either. Okay. So if you want to, you do have a slide coming up, but if you want to just somehow jot down in the margin, movement of planets are hard to explain, and jot down, and you'll see what I mean, apparent retrograde motion. I'll give you the slide, okay, soon. Movement of the planets are hard to explain. So, we're only in this class for, 16 weeks. That's not a long time. But, for instance, if we were to track, I think Mars is in retrograde right now. If we were to track the movement of Mars, we would see that Mars wanders against the background stars. Okay? Like here's a constellation. You see it every night, okay? And the planets will move. On the ecliptic, that line I showed you today, the planets are going to move on that. Why? Because they are orbiting the sun. And we see that motion. Okay? But the stars are fixed. Okay, so the word planet actually means wanderer. Okay, if you look it up and you think of that. So we're used to planets kind of wandering against the background stars. There's this normal motion that it says eastward, normal eastward, which I kind of get mixed up, but we call that direct motion. Okay? So if that's west, that's east. Usually we see the planets do this. Every once in a while, the planet goes backwards, and we call that retrograde motion. Now you have to watch it over, it's not the same night. You have to kind of plot it against the background stars several nights. Okay, retrograde. Okay, so here, this is, let's see, should I get this? June, July, that is direct motion. This right here, this backward motion is retrograde. and then we see it resume direct again. Okay? So, our model needs to explain that. And Ptolemy tried to explain it, and I'll show you how he tried to explain the backward motion of planets. So you do have this slide. So you heard me call this Ptolemy. The P is silent. Okay, so this is Ptolemy. You don't pronounce the P. And to me, when you look at historically how he fits in astronomy, he is like the last guy to think, and I'll go ahead and draw this, to think that the Earth, the symbol for Earth is a circle with a hashtag, to think that actually everything orbits the Earth. He is the last guy to think that. So when we talk about the Ptolemaic model, it's incorrect. In fact, I didn't emphasize this last night when I was covering this for my other class, but we called his model, a geocentric model. Why do you think we called it a geocentric model?
Earth revolves around.
That's right, because Earth is in the center, right? Yep. And he's wrong. But he took one last stab at trying to say why we see Mars go backward in the sky. And here's the Ptolemy model. Okay, so the Ptolemy model puts Earth in the center. That gray line there is the main orbit of a planet. Now remember, this is wrong. So don't go home and say, Mrs. Snipes thinks that the planets orbit the Earth. No, this is what Ptolemy said. Okay, so the overall gray motion is the regular orbit of a planet. So the way Ptolemy explained this kind of backwards is he said, all right, there's the overall movement, which is kind of represented here, and then every once in a while it will do these little loop-de-loos, and right there it's going backwards. And then it resumes, okay, and it goes like that. So all of this motion is direct, okay, and these little loop-de-loos right here, that is your retrograde. Okay, so that's how he explained it. He called them little epicycles, around little epicenters. So the thing about it is there is something called, and we're going to see it, we'll cover it on Monday, but there's, if somebody says to you, somebody says to you KIS, what does that mean? The nice version. I guess at the end, no, okay, wait a minute. Let me just tell you what I think it means. Keep it simple, stupid. Okay, right. So keep it simple, stupid. So actually that's a principle of testing your answer to your observations. And the thing here is this is not simple. This whole loop-de-loo thing is not simple. So he failed that. So I think this is a good place to end, a few minutes early. Okay, so chapter 2 will be due on Monday, but not chapter 3. Okay? Okay.
On our lab write-ups, do we have them?
Yeah, I'd love them.
Yeah.